This is part 2 of the 6G3. From the previous example, we were looking at the line of best fit. And now for this example here, we're going to use a line of best fit on this graph here by using the by eye method. And we're going to draw a line of best fit, and then we're going to find the equation of that line that we just drew. So now drawing lines of best fit, as we saw in the previous video, it was pretty simple because we were just putting lines that we thought can fit throughout the data points. But now we run into a bit of a tricky situation because we now have to find the equation of that line. And what's tricky about that is if I just drew my line of best fit, 2 points, 2 well-defined points might not always be given to me from that line of best fit. We might have a line and it doesn't actually hit any of these little cross intersections. So we have to take that into consideration. So when I draw my line of best fit, I actually think, and this is just, remember, this is a prediction, okay, that the line of best fit will start at this point here. I might actually do that in a different color. I might put it in red so it doesn't look like one of the points there. I reckon it's going to start here and it's going to finish here, or it's going to start at 0, 9. So when x is equal to 0, our y is 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's going to end at when x is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. That seems better. When x is equal to 10, corresponding y value is 1, 2, 3. So we've got our 2 points. And then with that, we draw almost like a dot to dot. And there's our line of best fit. So I almost hacked this in a certain way. I forced 2 points to be within my line of best fit, and it does look like a line of best fit. So when you draw your line of best fits for your questions, just make sure that if you're trying to find the equation of that line, you put 2 well-defined points. So now to answer this question, we know that it's going to equal, just sort of colors again, it's going to equal y is equal to a plus b x. We're trying to find a, which is our y-intercept, and we're trying to find b, which is our slope. A is very simple. A in this case, we know it's been given to us and we kind of forced it to be that. Our a value is equal to 9. A value is equal to 9. The b value, now before we put in the equation for the b value, I want to define which points are going to be x1, y1 and x2, y2, and we'll just do it from left to right. This is going to be our x1 and our y1, and this is going to be our x2 and your y2. So just a little note that if your x1 and y1 or x2 and y2 are weird decimal numbers or potentially fractions, try to avoid that if you can. We want to make this line of best fit as precise as possible, okay? And we've got someone trying to call me, which I cannot answer because I told him I'm with my year 11s making this video. So with the B, what I might do is I'm going to pause and I'm just going to close down my Microsoft Teams. Give me 2 seconds, guys. There we go. I had to close my Microsoft Teams down while I record this. All right, so we now want to get our B value. In this case, the equation for B, which is a slope, hopefully you should be getting the hang of this equation here. y2 minus y1 over x2 minus x1. We're finding the difference in our y's, which is here. We're finding the differences within our x, which is here. The difference within the y should be negative because we're now going down from left to right. We're going down. It's a slope that's going down. And all we're doing is just a straightforward substitution based on the points that were provided. So y2 is 3. Take away y1, which is 9. And there's a negative component. And our x2 is 10. Take away 0. And we know it's going to be the difference of 10 because we're going across by 10. 3 take away 9 in this case is negative 6, and 10 take away 0 is 10. So this slope, it's going down by negative 6 over 10 units, or when simplified, -3/5 units. So for every 1 unit this is going across by, it's going down by roughly 3/5. Okay, roughly 3/5, which is what, 60% of 1 unit? That seems about past halfway, yeah. So every unit that goes across by 1, it's going down by 3/5, and this is going to keep going until we get to this point here. So our equation, in this case, our y is equal to what our a value is, which is 9, minus, because we've got a negative slope, 3/5 x. Or 3/5 times x. You can put that x on top if you wish to, and that's all there is to getting the equation from that line our best fit slope. Okay, we forced 2 points to lie on the intersections. We found the intersection of the y and used that for our a value, and then using these 2 points we substituted it into our slope equation to get the slope, or the number in front of x, and just simply substitute it back into the template equation y equals a plus bx. Okay. So with this in mind, what's the purpose? What purpose is this used for? You've got this equation. Well, we use this equation from the data points. And remember, these are just random data points. Okay, there's no context for this right now, so it's probably seeming a bit arbitrary. But we use this to make predictions. Okay. And not all predictions we make with a line of best fit are equally reliable. Okay, it's the best thing that we have. The most reliable predictions are made when we use the line to make a prediction that lies within the range of data used to construct the line. Now, this is a confusing sentence because it doesn't necessarily make sense without context. I'll explain the 2 different types of predictions that we can make, and we can use this in our example here. But let's just say, before we get to this, I'll do a rough example. Let's just say that I roughly I did a survey, okay, and we'll go with that previous survey. And I got this height, and we mapped it out to the weight. So I asked, I don't know, 15 random people, look, what's your height and what's your weight? Obviously the weight and the height will start at 0 and it keeps going on. So when certain people weigh a certain amount, the height is going to be at a certain amount as well, roughly speaking. And we can assume that the heavier you are, the taller you'll be, roughly speaking. There might be some people that might not weigh a lot, but they're really tall, or might be really short and weigh a lot, like really stumpy. But the main aim I'm trying to show you is that there's this trend of some sort, that the heavier you are, most likely the taller you are as well, assuming that you exercise and you have a good diet, yada yada. Okay, I'm just trying to show you a trend. I'm not trying to make rude generalizations. I should have done a different example. That's all right, let's go with it. And then we make this line of best fit that goes across like this. Okay, now I use this line. Okay, let's say this equation is some random equation that I'll make up, and let's just say that it is y is equal to, let's get a new layout, y is equal to, I don't know, 15 plus 25x. Now let's change it in regards to height and weight. So height, or h, is equal to 15 plus 25w. Now remember, these numbers are just made up. I'm just making them up, okay? I have no idea what this is. We use this equation. We've got this cool equation. And we're then going to use this equation to predict the height of someone if given a certain weight. The only problem with this is that these data points, the starting point roughly being here and the ending point maybe roughly being here, or this one. The only problem with this is that what happens if we give a weight that is unrealistic? So say for instance in kilograms, let's say we put in someone weighed 900 kilograms. 900 kilograms. Well, if we have someone that weighs 900 kilograms, we put this into here, we're going to be predicting a height that's really, 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 really tall. But that's unrealistic. That doesn't make sense because we don't have people that weigh 900 kilograms or has a height of whatever this ends up being, 25 times 900 plus 15. That's impossible. So the reason why this line of best fit, or this equation that we get, is awesome is because it can make predictions within this range here. Okay, so if we have a weight of someone that weighs around here, we can predict that their height using this line is around here based on the data points that have been given to us. However, if I start making weight predictions that lie outside of this range around here, we're going to make height predictions where this line will keep going theoretically up here. But this realistically doesn't make sense because we can't make predictions of someone's weight that's really heavy as opposed to someone's height, which is really tall. There might be odd circumstances where this is the case, but there's only a finite height that we can be, okay? And this is the difference between what we call interpolation and extrapolation. So predictions are far less reliable when we use a line to make a prediction that lies outside the range of data used to construct that line. This is because we are working beyond the range of data used to construct that model, and we do not know if the model still applies. We have no idea if this model still applies if it keeps going. We might know it tapers off and it goes something like that. It might reach a plateau, but we're making this prediction that this line keeps going on forever. Okay, so interpolation is using the model, so this line that we have, to make a prediction within the range of data used to construct that model. So if we are making a prediction of someone's height within this range here, say for instance there, we can predict their weight. If we want a little bit heavier, we can predict it, and we can keep going within this range, okay? The moment we step out of the range from both ends, okay, we can't make a prediction that someone that weighs maybe 2 kilograms will be the height of some height around here. That doesn't make sense, okay? So it works both ways. So when we go beyond that, we are doing an action called extrapolation. And we're using the model to make a prediction that goes beyond the range, beyond being both sides of the data to use to construct this model, okay? You will definitely see these two, interpolation, extrapolation, pop up within the data field, okay? It's a lot of information to take in, admittedly, but it's good to get some insight as to what these two things are, okay? Because at the end of the day, all right, at the end of the day, what we're doing is we're getting some data, we make a line that fits best with this, and then with that line, we make assumptions based on that data set using that line, okay? If we go beyond that line, it's not reliable, so extrapolation is a less reliable process than interpolation, and we don't want to do that. So we want to stick to interpolation in a real life manner, okay? So let's look at this example, okay? Let's look at this example here to get some concept of interpolation and extrapolation so we can get some better intuitive feel behind it, okay? This video might go for 20 minutes. Let's see if we can go below 20 minutes. So a straight line has been fitted to a set of data that recorded the velocity in meters per second of an accelerating car at time t seconds. Okay, what does this mean? This velocity is just another fancy word for speed, okay? The speed of a car. And if the speed of a car increases, the time it takes will also increase as well. It's proportionally in tune with each other, roughly anyways. And that's what these little dot points mean here. So at time is equal to 0 here, the velocity of a certain car is at 15, 16, 17, okay? As the time goes across by 1 second, we can see that the velocity, the speed, is now at 20 meters per second, so it's going faster. It might slow down a little bit here and then go faster again, and it's going faster and faster. So acceleration is going up, so the velocity is going up as time goes across, okay? Very physics-based, but you don't have to focus too much on the context right now. We will later on when we do an interpolation, extrapolation, but let's just look at the equation for now. What is the car's velocity at t or time is equal to 0? So A, we're trying to find out what V is. We're trying to find V when the time frame, when t is equal to 0. So we're trying to find the velocity when time is equal to 0. Now that's simple because we can just look at this graph and we can say it's 15, 16, 17, let's say 18. So velocity V is equal to 18. And what's the context? Meters per second. So at this initial point, the car's velocity is at 18 meters per second. Okay? Very, very simple stuff there so far anyways. The next question is saying that the slope of the line can be used to find the car's average acceleration in meters per second squared. What is the value of the slope? So this is saying here that at time equals 0 and at time is equal to 5, we can see that there is this change of acceleration. It starts at 18 meters per second. In 5 seconds, it is now at 25 meters per second. So we know that it is sped up in 5 seconds. But what we're trying to find out is, what is that average speed, okay? Because we know it kind of goes a bit quicker and slows down, a bit quicker again, slows down, a bit quicker, but the average time it takes to get from 18 to 25 is what we're going to work out. And that's what we do by finding the slope. But the first thing we need to do is find two well-defined points. This one right here is at 0, 18, which is what we found here from question A. And we'll use this point, this last point here of 5 and 25. Okay, so 0, 18 and 5, 25 are our 2 points. This one here is our T1 and V1, so the time and velocity. And this right here is our T2 and our V2. Time and velocity. So question B, to find the average acceleration, we're just using that slope. We're just using that slope formula. And this is equal to V2 take away V1 all over T2 take away T1. So remember, it's Y2 take away Y1 over X2 take away X1. We're putting the real context now, velocity and time. And simple, straight substitution. V2 is our 25. V1 is 18. So the difference in the V, so how much is it going up by? And we're going to divide this by the difference in time. In this case, it's 5 take away 0. We know the difference in time is 5 seconds. It takes 5 seconds to get across. So 25 take away 18 is 7. And 5 take away 0 is 5. So our velocity in this case is 7 over 5 units. If we want to put this in straightforward decimal context, this is the same as 1.4. So the average, the slope, it's going up by 1.4. So in other words, for every second, on average, for every second that this car is going across by, every second it takes, it's speeding up by 1.4 meters per second, okay, on average. It might do different things. It might go faster and slower at different points, but on average, from this point here to this point here, it's sloping up by 1.4 units. So the question is saying in word format, what is the value of the slope? Therefore, the average acceleration, I'll just put ACC for short, is 1.4 meters per second okay, and that's where that meters per second squared comes from. 1.4 meters per second squared, because we're getting this meters per second as a rate to how long it takes, time in seconds. We're getting very physics based right now, okay? As long as you can get this number 1.4, that's one of the main aims, okay? Getting that average speed. Question C. I'm hoping I haven't lost you guys by now because I know this is quite a lot to take in. Question C, we're looking at write down the equation of the line in terms of v and t. Okay, this is simple because we found our A and we found our B. So let's change color. V is equal to A plus B t. We found what our A is. We found the v-intercept. We know what our B is. We found the slope, and it's a simple substitution. Our V is equal to 18 plus, because it's going up from left to right, 1.4 t. And there is our equation. We did all the hard work in the previous question to answer C. Alright, let's take this home. Question D. Use the equations to predict the car's velocity after 2.5 seconds and after 7 seconds. So we've got this trusty little formula now that we can use. And there's V equals 18 plus 1.4 t. And what we're doing is trying to find the velocity when the time is at 2.5 seconds. Now let's just backtrack. 2.5 seconds is around here. So at 2.5 seconds, we're trying to find the velocity at this point, and we're just trying to match it up to here. Now we've got the formula, we've got this line formula that we're using, but more importantly, I'm trying to show you that this prediction that we're making at 2.5 seconds lies in the range of 0 to 5. And when something lies within the range, we're interpolating. But for now, V is equal to 18 plus 1.4 times 2.5. 2.5 being from the question, 2.5 seconds. And then when we work this out, this ends up being 21.5 meters per second. So in 2.5 seconds, the velocity is at 21.5 meters per second. And in this case, we are interpolating. This is interpolation because it's inside that range. But then when we look into, not E, that was DI. When we look into i.e. 7 seconds, we're trying to find the velocity when the time frame is at 7 seconds. We are extrapolating. We're extrapolating because our range that would be given for this information is at 5 seconds. So if we go beyond that to 7 seconds, which is around here, our last data point is here. Okay, and then technically you can say that this line keeps going and going and going and going and going, but in real life, cars or vehicles or whatever it is, it's an accelerating car. Yeah, it's an accelerating car. Cars can't go, for normal standard cars anyways, can't go that fast. So if we keep making the prediction over time, provided this line that keeps going and going and going, we're extrapolating. We're making a far less prediction of what the speed of the car should be because it's going beyond our range. So the velocity is 27.8 meters per second, which is extrapolating. Okay, so we're interpolating because we're within the range. We're extrapolating because it's outside of the range for time. So question E was what type of predictions are used, and D, that was interpolating and extrapolating. And question F, when will the car's velocity be 30 meters per second? Now it seems a bit, again, we're extrapolating, we're going beyond that predicted range, but right now we're trying to find t, which is our time frame, when our velocity v has been given to us as 30 meters per second. So we're finding t when v is equal to 30 meters per second. So we know that our equation velocity is equal to 18 plus 1.4 t, and we are trying to look for, when v is equal to 30, we're trying to look for our t value. Now you can use algebraic skills for this, or you can use a class-fed calculator and the solve function to get a time frame. And that's what I'm going to do here. I'm going to grab my class pad. I'll move this across. Go to main. And we're going to use the solve function. Remember, keyboard, math1, solve right here. We're going to type in the actual equation itself right here. 30 is equal to 18 plus 1.4 times, we can just use x on your keyboard. You can just use x as long as you answer in the context of t, comma, and what are we solving for? We're solving for x. So remember the comma and the x, close the bracket. Your answer is 60 over 7. Let's put this in decimal format. 8.57. So it's going to take approximately, it's predicted that it will take 8.57 seconds. Now there's a question asked this in decimal format. Not necessarily. So t is going to equal 8. Let's get this up again. 0.57. Just you round it to 2 decimal places. Just as a standard rule, seconds. And that is 6G3 part 2, nearly 27 minutes. A lot to take in, a lot to learn. Definitely ask me questions, okay? We get into the nitty-gritty tricky part. Nitty-gritty tricky part, I just made that up. We get into the nitty-gritty, yeah, of course I was gonna stuff it up again. Get into the tricky part. Okay, I'm expecting more questions from you guys. We've got one more video after this and then we'll wrap it up for chapter 6, and we've got 2 assessments after this, okay? In the meantime, check your logbook or log sheet to see which questions you need to do, and I'll see you in the next video.